This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
You don't actually understand why you're doing that. So then you get an assignment and you start like, okay, let's crunch the number for the lecture slide, but never really think about why.
Yeah, that's true. Take a step back. What are we doing?
So yeah, I thought it's important to actually give them an overview first, and then get them to think, because a lot of the time that when we deal with this multidisciplinary interface, you spend so much time getting a result, getting an answer that you think it will work. It gets bashed up by every single other, discipline. It's like, nah, it's just so hard. So we learn the easy way is to actually talk through the result first,
Yes.
and try to get it to work.
Yeah, get some feedback.
Iterations of calculation, it's just too hard. Every time you do it, and then you talk to a discipline, do it again, right now. So
Yeah, get it narrowed down before you do it.
correct. So yeah, a bit more. I guess that's probably the main difference between uni and industry is a bit more interaction between the different teams. You sort of understand your own area or expertise is probably step one, but then you really need to understand other people what they really want, then come back and use your
I think that's worth mentioning today as well to the students. Because it's good to understand that context.
You realise you're going to contribute more time to me, right?
Yeah, about 5 more minutes. Yeah, no problem. Okay. Okay, good morning and welcome everyone. Thanks for making the trip, especially 9 a.m. daylight savings time, so I'm sure everyone braved the cold morning this morning. So we have our third last lecture for construction engineering, and a really valuable and important one. We have a special guest, Sean, with us today. Sean's from Aurecon. He'll be presenting a range of projects that he's worked on that are really relevant to the task that you've got coming up, Task 4, and showing us a few details on some pretty exciting bridges and similar projects. So thank you so much, Sean, for taking the time. Yeah, please. So.
Hi guys. My name is Sean Young. So I work at Aurecon Melbourne office. I'm a senior engineer specialized in bridge and civil structures. So today's presentation, I'd like to go through 3 sections here. So the first one is a bit of an overview of my 10 years work experience as a civil structural engineer. Then I will step through some of the interesting projects that I have done in the last 10 years. The second section, as a few mentioned, that you guys have an assignment that is quite relevant to bridge design. So I've been requested to, actually I got his permission to help you guys as much as I can. So I'll be handing out a bit of an answer section hopefully. So hopefully you guys can learn a few things from this section 2, which is a design of a simply supported single-span pre-stressed super T or T-roof bridges. Then the last section to wrap up, I will provide some career advice. It's understood that you guys are in your final years and looking for opportunity to join the industry or graduate. So based on my own experience, I'll probably give you some advice in terms of how to network with the industry, understand the work arrangement, and also how to apply for a job. So a bit of myself. I graduated in 2012, end of 2012, so almost exactly 10 years now, with a Bachelor of Civil Engineering and Bachelor of Commerce. And I obtained my chartered status. Oh, okay. Do I just close it?
Yes.
Okay. Yep. So, and then I got my chartered status in 2017 after about 5 years of experience, and then I got the registered professional engineers with the Victorian government in 2022. So there's a few photos of me, working on site, and the bottom right one is the first time that I'm actually important enough to get a Photoshop, so I thought I might share with you guys. The next photo, the next table is a list of job roles, area of practice, and project roles and duties that I've done in the last 10 years. I'm not going through each one of them, but I thought it's actually a really good reflection of myself. So it gives you guys a very brief idea of how a graduate can then slowly develop and then take a few detours, but then specialize in something that you actually enjoy doing. So it sort of talks about your company role, and then when you join a project, what kind of duty you're responsible for, and then the estimated project value, because that's always one aspect that you look at the project and the things you do. So I really want to highlight that the big transition that I did was from the client side, joining the consulting. I do actually enjoy a fast-paced working environment because I feel like time goes faster and I learn a lot more. But having the background, understanding and work experience from the client side, that gives me a really good understanding of how the project manager thinks and how my current client thinks, so I can better interact with them and actually obtain a mutual understanding when it comes to project delivery. Okay, so some of the project highlights. So first year of my, after I graduated, I worked in Kimberley region in Western Australia. So that was on site, doing project delivery. So I did a bit of road widening, pavement construction, resurface. I started as a site engineer or graduate engineer, and then slowly transitioned into a project manager, managing up to about $1 million project. So as you can see at the bottom, this is a single lane bridge in Kimberley, which is about 50-60 kilometers outside Derby town center. So this is the only access for the town center to get all the grocery supplies, petrol supply, all the equipment. And there was two trucks collide into each other at night, and then the fire and then the collision damaged the road barrier and the road surface. So temporarily, there's no access for the traffic. The bridge was shut down, and we had to do emergency repair. So I was the project manager that issued the urgent tendering package, and then engaged with a local contractor, and then stayed on site, and then organized the traffic management, and then delivered the repair. So which is quite rewarding at the end, but it was pretty tough work because we have to get up at like 4 o'clock, and 6 o'clock there was a toolbox meeting, and we walk straight to 5-6 o'clock in the afternoon, and then we do a quality assurance process at the end of the day. Then I spent about 1.5 years in pavement dipping and rehabilitation design, and also concrete testing. So this is quite a unique area that not many consulting firm does. So this is more from like asset owners' perspective, that they needed the testing result to understand how the overall asset performs and why certain types of the problem actually occurs. So this type of pavement dipping investigates shoving, settlement, net crackings of the asphalt surface, or gravel surface, or some of the bridge foundations, and as you can see that you got all this concrete testing going as well, so sampling and testing as well. So this gives me a really good understanding of, in terms of during construction, what kind of testing is required to make sure that you understand the design parameter, and what kind of rehabilitation works that you may be doing in the future to rectify some of the issues. And then I did a bit of detailed inspections. So as you can see, this is as small as it can get. I did some timber bridges for the local city councils, and then also some multi-span steel and concrete composite rail bridges for giant mining companies. So these bridges facilitates the transportation of mineral from the mine site to the ports in Pilbara. So you can see that the trains are operating 24/7. If if the railway shuts down, they will be losing hundreds, millions of the dollars. So it was quite an important task for us to get in there during the rail shutdown and then perform the asset inspection and then come up with any sort of repair or maintenance strategy and then get out. Next one is a bit of a, probably more relevant to you guys, finite element model. I'm sure you guys did a few projects in uni. So a few things I like to talk about is when I was a student, I always thought that master in a design program and then model everything in a design program like a Strand 7 is probably the coolest thing in the world. The first project I got in was a consultancy. My project director told me that start with a stick model, a plate model, and a solid model, and then I want you to achieve exactly the same result before you proceed any further. Then once you achieve all the result, I want you to use the stick model and then with varying parameters and justify all your results and then go ahead with your analysis. What does that mean is when you're in consultancy, time is always one of the critical elements. So you don't get monsters to sit there and then enjoy your beautiful model and play with it. You get the stick model, you get the same result, and then you vary your parameter and trying to get the best result for your client. And so in addition to the conventional sort of structural model, I did a bit more soil and structure interaction analysis. So this is when we get the support from the geotechnical engineers and we get the bidirectional soil stiffness springs. So that gets attached to the structural elements, and then you can analyze the deflection, the settlement, and construction sequencing, and also secondary issue like the force and displacement effects. Some interesting project I did. So this was done in 2017 to 2018, the Sydney Barangaroo station. Different to a conventional or typical station, this station is actually underground, and as you can see, the water table is literally at the road surface. So this is probably the biggest reinforced concrete bathtub you can see in the world. So, typically you will get surcharge load from the train stations or the reaction from the train station above the underground structure, and then you just have to design the underground structure to sort of support the reaction. But in this project, the design of the underground structure is a package of its own, because you have all the soil pressure on the side and as well as the hydrostatic pressure, because the water table is so high, and the design groundwater table during a flood event is even higher. So making sure that this bathtub doesn't actually get floated and then just flushed away, it was quite a challenge. We have to use, we have to basically consider all the dead load with safety factor, and also rock anchor into the foundations underneath. The next project is Armadale North Lake Road. Now, in terms of the project value, this is not as significant like billion-dollar infrastructure work, but it's a small, relatively small project that has everything that I want to show as for like a construction and infrastructure project. So this job has a multi-span bridges above the roundabout, and then underpass, and also a twin single span bridge which forms a roundabout above. So it's a bit of a cut and dive and viaduct solution here. So I was the structural designer for two of the underpass. One of this is the underpass 9472, the trapezoidal, and there was the other one was the arch underpass. And I was also the designer of bridge 1893, and I did the verification of the twin single span bridges here. The reason I want to show this one here is a good example showing that a project has been delivered on time, on budget, as well as incorporating all the Aboriginal art, which sort of achieved a community harmony, and everybody received the result that they hoped for at the beginning of the project. Obviously, 90% of the time we don't. So this is probably like a good success in my career. The next one is the tender and detailed design of a multi-billion-dollar contract, Metronet, Western Australia. So this is by far the biggest tender I have done. Typically, a tender lasts for about maybe 2 weeks to about a month, give and take, because you only provide a concept and then you work with your estimator and then you come up with a package and an estimated price and then you go for the tender. But because this package is so big, we had about 100 engineers across different disciplines. Structural engineer was only 10 of us, and then there was like 90 other engineers, rail, civil, earthing and bonding, electrical. There was all sorts of engineers. We get together as a group, 100 of us, including an estimator, of course. So 100 of us got together and then formed the Design Alliance, and we spent 4 months full-time working on this tender design and up against another team with the similar size of the designers. We were up against them, so 1 versus 1, and took about 4 months to finish the design, 300 gigabytes of data, 6 boxes of the contract document, then delivered to the client. And we managed to win this one. So that was a really good success. It was more like, okay, you lose, you run out of job for the next 3 years, you win, you're going to be busy for the next 3 years. So that was a very interesting experience for me. And so we then proceed with the detailed design after we won the contract. The detailed design consists of 2 new stations, 4 bridges, and 2 modifications to the existing bridge, about 17 kilometers new passenger rails. So within the Thornlie to Cockburn line of Metronet, I then managed the structural package, which one of the structural packages is the steel truss pedestrian bridge over rail. So this is probably the last steel truss bridge in Western Australia, because after we won the contract, the project specification from the client side got an update saying that the client maintenance team no longer want any steel structure over the rail anymore. The reason being, to maintain the steel structure, every 20 to 25 years they have to paint over the rusty area. And it is very difficult every time you have to organize a rail shutdown, the access, the maintenance work, the safety issue, and there's cost. So that was the last project that we actually managed to get across the line for the client. And it was a very interesting one as well, because the client then said, instead of having us go and maintain it every 20 to 30 years, we would like to have 120 years design life. So how do we achieve that? So we had to actually do a combination of increased corrosion thickness and also hot dip galvanized coating. So I'm not sure if you're familiar with the hot dip galvanized coating. So this is a better product than just conventional paint, which only lasts for about 20 years. Hot dip galvanized coating lasts for about 50 to 60 years, depends on the thickness of the coating that you can actually adhere to the steel surface. So in this project, we had a steel truss, the main truss spanned over the rail, and the single span is about 44 meters, as you can see here. Now, the challenge we get during construction was that the procurement of the steel truss, we can build a 44-meter long steel truss by welding the square hollow section together. However, you won't be able to achieve the hot dip galvanized coating because the facility can only accommodate up to 16 meters. Therefore, we had to actually divide the main truss into 3 segments with splice connections. So that adds quite a bit of complexity to structural design. Because what happens is you're trying to introduce a splice connection in the middle of the bridge that will encroach into your minimum vertical and horizontal clearance underneath, as well as inside your steel truss. So there's a lot of the geometric play around, and you're going to make sure that every time you change your geometry, you change your entire design model and you add more self-weight to the truss. And that then turns yourself into an iteration of calculation that you really don't want to do when you don't have time. And a bit of interesting background for this job is, as you can see, the blue dotted line. So at the start of the project, we're trying to be a bit, making the community happy. So we're trying to say a little bit of difference in terms of the ramps. We're trying to actually divert the ramps on this side and then trying to steer in front of this beautiful wet land or lake reserve. But it was such a nightmare to get agreement with the property owners. They reckon people standing at 9 meters tall, looking at their front, the facade is probably a bit of a privacy problem. So we then had a bit of a communication with the construction and local consultation. We agreed that we would do a mirror image and then had a construction of the same sort of span on the ramps on the other side. The next one is one of the projects that I'm pretty proud of, which is the longest single span precast pre-stressed T-Rock bridge in Australia. So I finished the design in 2020 and then the construction was in 2021. There's a beam lifting video that is available on YouTube. I was literally, on that morning, I was literally standing on the existing bridge. I had like a little chair for fishing and I just stand there and then took the video myself as well. It was longer than I thought. The video was only a minute, but I was there for like 4 hours. It was very slow motion, but it was quite interesting at the time for me because I have never seen two crane and then one of the biggest 500-ton crane on the other side, like working together and trying to get things in place. So I'm not going to go into much detail because we're going to discuss the detailed design of the bridge in the section 2, but feel free to have a look at the video. The last one I want to talk about is the level crossing removal project. So this is the first job I did in Melbourne. So since May 2022, so I'm the structural lead for both level crossing removal projects at Robinson Road and Fitzgerald Road. It's a bit of a unique experience in terms of how the design interacts with the contractor. So we'll talk about the construction support at the end of the design section. Okay, who's ready for some design? So this is the fundamentals. Let's start with some fundamentals. Simply supported bridge versus continuous support. So what's the difference there? The fundamental difference is when you have a simply supported bridge, you basically look at the critical sag moments at the midspan, and you will be able to size the shorter span based on the less critical bending moment. Whereas the continuous support restraint condition, you will have critical sag bending near the midspan, not exactly at the midspan, slightly to the left, and then you're going to have a critical Hawke bending moment at the intermediate support, and then another less critical bending moment here. Now, fundamentally, the principle is the same. However, looking at these two, what it's telling us is that when you have a sag moment, your compression is at the top, your tension is at the bottom. So you will size the number of your pre-stressed strength based on the critical sag. When you have a critical Hawke at the intermediate support, what that means that you will have your tension at the top, your compression at the bottom. That means that your strength is now no longer in the tension zone. So you're going to rely on a link slab or some sort of strengthened section with sufficient reinforcement to redistribute that hogging moment. Okay, so let's talk about a bit of a multidisciplinary interface. So I was just talking to Phil, and Phil thought it's good to actually touch base with you guys. A lot of time that we learn in uni is, we get an assignment, we're trying to do number crunching. It is good, it's the fundamental of what we do, but multidisciplinary interface at workplace is probably more important because you can do a lot of the iterations, but as soon as you finish it and then you talk to one party and they will say, no, this is not what we want, and then you go and talk to another team, they will again tell something different. So it's a bit of like the movie Inception, the Leonardo's movie. Imagine that structural design is your real world that you are comfortable with. Then you have to dive into other people's section and try to understand what their requirement is and what they want. And then you dive deeper and deeper with the previous owner, and then you're trying to gather them all together and trying to come up with a solution that is within your structural package and then complies with all the requirements here. So this is the typical cross-section of a single span bridge. So as you can see, we have a minimum horizontal envelope, clearance envelope, and a vertical clearance envelope that we have to design to. We have a rolled over the rail profile on the top, and then we have screens to prevent people throwing rocks onto the rail track or trying to jump off the bridge. So there are a lot of aspects to it, and then this is a typical cross-section showing how the Super T bridge looks across the transverse direction. So design of the bridge superstructure typically has the serviceability limit state design and ultimate limit state. Ultimate limit state is probably slightly more straightforward because all we're trying to do is we model the bridge, we get the design action, and we're trying to make sure the ultimate limit state factor design action is within the calculated capacity. Now, serviceability limit state design is actually more relevant to multidisciplinary interface. So for example, the deflection of the bridge superstructure cannot encroach into the minimum clearance envelope. When you have a live load going on your bridge starts deform. And then that deformation can never encroach onto the train, otherwise they will be touching each other. And the serviceability limit state design also talks about the crack control requirement for a typical reinforced concrete, so which means that the durability and performance of your bridge can last for the design life that your client really wants. For example, AS5100 specifies 100 years, and
sorry, keep going. Just finish it.
And then some of the clients start asking for 120 years design life now. Oh. Cool. All right, so modeling. So why do we have stick model or the grillage model, the 2D grillage model? I recommend you guys, if you guys ever want to specialize in bridge engineering, this is probably the Bible and the first book that you want to find answers that you're after. Oh, how do I go back? Previous. Yes, so the screenshot at the bottom is a 2D grillage model. Why do we have a stick model and the grillage model? So the stick model always gives you the first instance of where the critical load is. For example, the critical sag, the critical shear, critical halt. Then the grillage model enables you to actually understand how the load gets distributed from the traffic loading to your primary elements, for example, the longitudinal beam. So instead of having all the point loads on a stick, you now get to distribute that load over width. There are different programs that you will be able to utilize. I'm not sure what you guys use in uni, but there are plenty of tutorials, so I wouldn't stress about it. That's something that you guys will be able to learn as you go in your career. It's more about the principle and understand how things operate. So for example, I'm familiar with the Autodesk Structural Bridge Design program, but I should be able to operate in different environment regardless. So the next one is a bit of a detail. So when you set up your grillage mesh, you need to actually define how individual elements in your model actually interacts with each other, which means that you will then consider the stiffness of the element, the cross section, and the amount of the reinforcement and strength. So this is an example of the longitudinal grillage section property. This is the beam, and we have the solid end diaphragm, hollow sections, intermediate web, and also the strength that's going to be running at the bottom of the beam. And the next one is So once you have the beam set up in your first, for the longitudinal member, then you have to assign the property on the Greeley model. And then as you also have to introduce the transverse member, the end member, and the dummy member. Now what the dummy member, the edge dummy member does is it sort of introduce the boundary of your bridge, but it doesn't actually have a stiffness. So we'll put a very tiny little 5 mu by 5 mu concrete that doesn't actually attract loads. And then that helps you with any sort of superimposed load, for example, the barrel, the edge barrel loading, the screen, any sort of like edge curb upstand that you will be able to put as a superimposed dead load that doesn't actually contribute to your structural capacity. Then once you have a model, you need to think about what kind of the loading that you will be able to act on it. So that comes down to what kind of traffic loading you have to define. So you will then start with traffic lanes. And as you can, well, you couldn't actually see that now. So this is actually the pedestrian loadings on the edge. So we have to define the traffic loads and then the carriageways and then the bearing locations, the ones in the red dot. So between the bearings, that's your primary the longitudinal beams. Once the lanes are set up, then you will be able to apply traffic loads as per the AS5100, as well as any additional vehicles that is specified by the asset owner. So a load combination as per the 5100, and as you can see, this is one of the examples that's showing different wheel load that is side by side in terms of how to sort of compile them together on the same 2D model that you have. Typically for a structural package, as a designer, you will then prepare a list of the design assumptions to enable any reviewer or independent verifier to assess your design. So because you will get about 3 or 4 times longer than the reviewer, so you get to actually do a bit of a decision making, optioneering. So by the time that the reviewer receives your package, they need to actually know what kind of design assumption you have made. So instead of trying to optioneering like a complete independent verification, they get to know what assumptions you have, and then they will make their sound judgment based on this. Okay, so once we finish the modeling, we come to a bit of a design or beam detailing, if you like. So on the left, this is an example of the critical design actions for one of the primary beams. So this is the bending moment, associated shear, and associated torsion. You will also be able to get a critical shear with a corresponding torsion and corresponding moment, and you can also get the peak torsion, critical, and a corresponding shear and corresponding moment. So there are different load combinations and different output that you will be able to extract from the model. So interpreting the model is quite important, so you don't miss any sort of critical design load cases. And based on the bending moment, you will then be able to determine the number of the strand in your tension flange that is required, and then you will be able to size the reinforcement, the shear, the thickness of your web based on the design maximum shear that you have. So the example of the calculated structural capacity, and you can show that along the entire length of your beam, you will be able to see the bending moment that is within the capacity. Now, probably worth mentioning, this is by far the longest single span pre-stress beam in Australia. Not sure about South Hemisphere, but definitely in Australia, because we're absolutely hitting the manufacturer's capacity. So this is probably the biggest single span bending, sag bending moment that you will be getting, and that was a very nightmare to construct at the start. Everybody was learning new things, and it was a bit of a construction challenge for us as well. As you can see, there are EURS bending capacity. There was the shear, torsion, and moment combined effect. I've listed the clause in the AS5100, so you guys can actually see the formulas and you can do a bit of number crunching. But once you get familiar with the process, you will be able to actually calculate from the beginning to the end of one end to another end of the beam, which means that you don't have to throw all the reinforcement and strength along the full length of your beam. You will be actually trying to reduce some quantity for your client as you go. So this is where the truncation point happens. You have a splice and you have a reduced size of the reinforcement. Now, in this case, we also have to look at the beam deflection. So when the beam first gets manufactured, this is the blue line that you're seeing. It's hogging a lot because there's no wet concrete, there's no composite deck, there's no superimposed dead load. As soon as it gets the wet concrete, it starts sagging a little bit, but it's still hogging overall. And then in the long term, after the long-term pre-stress loss, concrete shrink and creep, we still want to make sure that overall the beam is still hogging because we don't want to encroach into the clearance envelope underneath. So a very important lesson that I have learned is that you really want to have a bit of fat in your design, so allow contingency. Please don't do it like when we were in uni, we're trying to hit the perfectionist 99.95 utilization, tick the box. Don't do that, because things are very likely to go wrong. For example, the contractor might accidentally set the bearing height 50 mils lower. What that means is along the 50 meters, you will get 50 mils thicker composite deck, which means that your superimposed dead load will be higher. It will basically just tick the box and then you go 122%. Bang, you failed. So always allow a little bit of fat in your assumption. You can always try to allow for 100 or 150 mils additional wet concrete during construction to make sure you capture all possible scenarios. The next one is, so we basically just talked about, in a nutshell, what the first step of grillage modeling or design of a bridge structure looks like. But in addition to that, there's a lot of other aspects and a lot of other elements that we can do. But due to time constraint, I won't be able to go through individual one of them, but they're all critical elements that you guys should consider if the information is made available to you guys. So I've made some reference in the bracket here. You guys will be able to read in AS5100, and I've put 3 examples here. So the first one is the cover. So cover is one of the very fundamental but critical element in construction. So what does that mean is, concrete cover, when you have minimum concrete cover, it means that you're going to have sufficient amount of reinforcement at the concrete surface to provide crack control. Now, if this cover is too little, that means that the crack width, your reinforcement is too close to the surface. That means the moisture can ingress through the concrete, and then you end up with rusting, expansion of the reinforcement, and have all sorts of durability problems. So you're going to achieve the minimum cover. But there's also a maximum cover, because if your reinforcement is so far away from your concrete surface, that end up being another problem is you don't have enough control. That means your crack width will open up, and then you're more likely to have a problem with cracking or hairline cracking on the surface, because that will be just like mass concrete. The next one is the cantilever flange, the bending. So imagine this is the beam and you have the flange on the side. Why do we have to do this? Because when you imagine the construction sequencing, you have the Super T manufactured, transport delivered to site, then you have wet concrete laid on top of that with formwork. So during this process, the wet concrete does not contribute to any construction or any structural capacity. So the beam itself has to sustain all the wet concrete load. So the flange that is basically cantilevering from your web is now taking all the cantilevering load. So having different models set up now, it helps you to understand what the deflection, the SOS deflection is, and also the ultimate limit state bending. So you will be able to size the ligatures and the reinforcements accordingly. And then the last one is looking at the detailing of the end diaphragm. So there's a example in AS5100 Part 5 2004 commentary that goes through the example of how a strut and tie model, which is basically what this picture is saying, how the strut and tie model works, and you guys will be able to follow that example and work out what kind of anchorage stress that you will get within the big concrete block at the end. Okay, so that was basically the summary of design of the superstructure. So we have the superstructure, we have reactions from the superstructure. Now we're talking about the substructure, how the load gets transferred or resisted by the substructure. Again, similar to the superstructure, your substructure has also got a list of criteria, put it this way. You simply can't just randomly pick a type and then just say, let's do the number crunching. Yes, it works. You're gonna get really regret with that, because it depends on the retained height, the site constraint, and the construction team's input. For example, what kind of contractor is available in the market and what kind of plant is available. Then you will be able to determine the construction methodology, whether it's top down, whether it's bottom up, and the type of the wall with geotech as well as the construction team. So there are a list of requirements that you should consider before you dive into any modeling or number crunching. Okay, so similar to the superstructure, again, you have different types of models. So this time, instead of Autodesk SPD, I've used Strand 7 for the substructure. Now, there's a debate between using 2D model or 3D model and in the workplace. Sometimes when you have a relatively easy or less retained abutments, for example, if the abutment height is up to say 4 to 6 meters, then a 2D model may be sufficient with a very conservative assumptions. So you got to work with the geotech team. But when, for example, in this scenario, we have a retained height up to 10 meter, and we have a lot of the reactions coming from the superstructure. And the superstructure, it was so heavy and then had a bridge skew of 30 degrees. So the abutment was taking a lot of the 3D forces coming from the top. The 3D effect really needs to be investigated closely. So this is where the 3D model has been justified to be adopted in this analysis. So I guess the benefit here is we get to use the bilinear soil spring to look at the 3D effect and investigate all the secondary force displacement effects, and also looking at the load distribution, not in the longitudinal but also in the transverse direction. But obviously there's a trade-off because it's relatively time consuming, and anytime you change your cap beam geometry or you change your tie-in detail or change the retained height, you got to change the entire model. And there's always some noise in the result because you're creating a giant monster that you got to be able to control it. So the load combination, again, similar to the superstructure, you're going to look at what kind of load combination you have to consider here. We got the earthquake loading, soil pressure, hydrostatic pressure, if the soil condition is, cohesion soil. So and also you got the collision load from the rail or the road traffic, and then the reaction from the bridge superstructure. So this is a diagram showing you on plan, this is a skewed bridge. When there is earthquake loading or there is an in-plane rotation, what does that mean is instead of having a perpendicular action to the cap beam, you now have a skew force. You have a vector in X, you have a vector in the Y. So you will be able to actually analyze in two different directions. So back to the reason why we don't use a 3D model is when you end up with something looks like that. You got to be able to filter your elements during your design and look at the particular element in the particular plane to be able to size your structural elements accordingly. So having that experience and trying to create the family and the groups of different structural elements is actually quite important. And in additional to that, bridging between the gap of the the bridge superstructure and the bridge substructure is also another key element. So as we mentioned previously, we have to investigate the force, the load pass in longitudinal and transverse directions. So this is an example where you have the earthquake loading that is passing from the bridge superstructure to the substructure. And a strut-type model has been created, and then we will then size the reinforcement in accordance to this model. Then another primary aspect of design of the substructure is the design of the pile and the design of the cap beam. So the principle is the same. You have the design action from your model based on various type of the load combinations for SRS or EURS design. Then you will then size your piles with the calculated capacity that is greater than the design action. And when you look at the deflection, you look at the deflection limit, and you look at the anticipated movement of your foundation and the piles, and then you will be able to size that accordingly. Then in addition to that, the challenge of secant pile in this job was the starter bars coming up and the detailing as per 5100. There was a bit of a clashing, so we were invited to site and trying to tell them which ligatures, shear reinforcement can be actually sized a bit further apart to make rooms. So that's a bit of an interesting design and construction alternation on site. Okay, construction support. It's not the most glorious job or the part of the job of a big project. So this is when things goes wrong. And so what happens is, as a designer, you spend a few months or up to a year, you prepare a set of the IFC, so issue for construction drawings for your client. Then your construction team will take that on board and start talking to subcontractors and trying to do a procurement. Then a lot of the time, because, for example, post-COVID, a lot of the materials are not available. So what they're now seeking is alternatives or a substitution to the previous product that you specified, and changing the sequencing to save time, save cost, and provide a value for money solutions. So you basically, in a way, redesigning your structure to accommodate some of the construction decision, because design is always just on the paper. To enable the construction is your ultimate goal. You basically have to hold hands and then work through this process together. And they're not usually very happy, sections there, because there'll be, some debates and decision makings, and a lot of time you rely on your technical expertise and trying to reasoning with your client. So as you can see, I've put some examples that things can get pretty messy even after issue for construction. There are things that could be a design error, that could be a construction misunderstanding, and there could be just alternation. I've also just to give you guys a little bit of understanding of what kind of an interesting aspect that you might get is the case study I've prepared here. So a realignment of the water main during construction. So during design, we thought the best option is not to add the complexity of a water pipe to the bridge superstructure. So the utility team was pretty happy just tunnel it through under the bridge, like any other site would do, but the client has then requested the pipe to be relocated to the bridge level and then attached to the superstructure. Now, from a bridge designer's perspective, what does that mean? That means that you then have a retrofitting connection you have to design to your precast beam flange. So the first option that we thought that would be the preferred option is to sort of install the steel strap and then a steel sleeve, and then the steel pipe inside the steel sleeve along the bridge under the precast flange. So this will increase your superimposed deadlock to your edge beam, and it requires opening. So the pretty picture on the right, I actually enjoy drawing that. That's probably the most enjoyable moment of my construction support, is drawing all these nice hand sketches and then send it to a client. It didn't end up going to there, as you can see. The deal breaker. The design worked but the lifting and installation becomes too much of a trouble for the construction team. So we had to actually move to possible resolution number 2, which is embed the water pipe into the concrete pass. Now, I want to point out the fundamental difference here as a structural designer. When you attach a steel strap connection underneath, and then you have a sleeve, and then you allow for the movement of your pipe that is independent from your bridge. What does that mean is the movement of your bridge then does not impact your water pipe. Your water pipe stays as is, and then the movement of the bridge under braking load, under earthquake loading does not impact the performance of your water pipe, which is happy for the utility team. Now, when you're trying to embed your water pipe into the concrete pass, they move together. Not as happy as a structural designer wants, so we have to basically account for thermal expansion and contraction in the longitudinal direction and transverse direction, the differential movement of different abutments, and then also the selection of the pipe expansion joint now becomes so critical. So we end up having a bit of a back and forth with the supplier, and we source the right type of the water pipe expansion joint from a proprietary product supplier to enable that process, and then we come up with this solution, which was then adopted for design. Okay, so that's the overall of how a design of the bridge package would work. And in addition to the bridge design, we may also get design of tunnels, noise walls, retaining walls, and all sorts of different civil structures. So I hope you guys can, basically the principle sense is the same, so I hope you guys have get an overview of what it looks like. So at the end of this presentation, I'm going to talk about a little bit about the career and how to get a job. So Phil mentioned that some of you are in your final year, and obviously you guys are getting ready to find a job, and it's always pretty challenging to sort of wrap up your study and looking for a job. So I always like to tell everyone that is in their final years to actually understand your industry first. So don't rush yourself and jump onto every single job that you can see. I understand it's a lot of stress. I understand that you want to get into the market, but understanding and collecting enough information before your decision making is really important. Especially for civil engineering, we have so many different aspects. We have very different workplace environment. We have different type of the company that we can work for. So collecting those information, basically asking for everyone you know from the industry, what do you do from day to day? What do you see yourself in short term, medium? Everyone has their own idea and own preference. So understand your own sort of situation and understand what you might get into when you apply for this job is quite important, in my opinion. Then you will obviously make the self-evaluation, plan your career path. Again, I'm saying this, it looks easy, but I know it's very hard because I just been 10 years trying to figure it out, and it took me 5 years to actually confirm with myself that yes, this is the area I want to specialize in. It took me 5 years, so I'm not expecting you guys to understand that in 5 weeks or so, but the difference was that I was miserable for a good 5 years, and you guys can probably collect more information and do a bit more future planning now. The final step is probably just networking and apply for a job. So a lot of the people come up to me, the first thing they worry about is how much they get paid. Look, trying to understand that you're trying to learn from the industry, how much value can you create for your company is very important. You got to value the experience and the skill development in the early career, in the early stage of your career. Then you can talk about money. So focus on getting the skills that you want to develop and the kind of the work arrangement that you want to commit it to in the long term. Enjoy what you're doing. So take myself as an example. I was in a client side. I had a really flexible working arrangement during my graduate program. So I get to rotate through road alignment, traffic modeling, waterways, bridges, construction, different aspects of the civil engineering. But I wasn't too sure about my role as the asset owner or client-side engineer, because a lot of the time I don't get to make that decision. I do a lot of the contract management, I do a lot of the quality assurance, but I don't actually do design optioneering. And turns out that's what I enjoy the most. So after 5 years, I decided, look, I just want to do design. So I joined a design consultancy, and then I have been doing design, purely design since then. So that's where I enjoy doing the most. And yeah, time flies every day, and I actually learn the things I want to do in the long term. So I spent 5 years and make a few detours. I hope you guys will actually, gain enough information or early stage of your career, so you don't have to take as many detours as I did, and hopefully you guys get the job that you guys want. So that's the end. Any questions?
Any questions for Sean? I've got a quick one. You mentioned on the Super Ts you look at not only the design in service but also in transportation.
Correct.
Was Craighead one of those critical cases you looked at, or?
No, it was actually the transportation from the yard to the bridge site. So the reason that we have to look at it is when you look at the Super T in the permanent stage, you have the support at the bearing, the center line of the bearing. So your span length is determined. But during transportation, because you're now using the SPMT, the mover, the multi-span, multi-axle mover, so the supporting point might be at the center line of your the long axle plant. So what that means is your support now gets closer to the center. You will have a cantilever of your end of the beam. So what that means is that you will have cantilever, and then you will start having tension, too much tension on your beam flange. So the steel stress in your top flange start opening up and then start cracking. So we have to make sure that we limit the offset from the end of the beam to the support point during transportation, as well as temporary supports on site, to make sure that during the transportation and delivery prior to lifting to the permanent location, the steel stress is within the limit.
Okay, yep, that makes good sense. Thank you.
I have a question.
Yep.
It's more related to structural design. So
Sure.
I mentioned I noticed that in the simply supported bridge, apart from bending moment and shear, there are also torsion, which is induced at the two ends and the middle. So I'm wondering, because in the uni we are basically dealing with bending and deflection and shear, but not much more to torsion. So
Okay.
would you like to
Sorry, if we just repeat the core of the
Okay.
question for those online, they can hear it.
So
too. Yeah,
I think
thank you.
the question raised by one of the students here is during the study in uni, we do a lot of the design, basically looking at the bending moment or the shear force independently. But in the example that I showed, it was actually the combined shear, torsion, and bending. So I guess I guess that's your question, right? You're trying to understand why and then the difference. Okay, so there's a little bit of background to it. AS5100, if you guys look at the 2004 code, so 2004 code, there is an empirical method for design of the beam against the shear actions. So they provide you a very conservative shear force and the shear capacity that you will be able to use the formula, and then you will say, based on this formula, this is my calculated shear capacity. But in the 2017 code, we have been introduced the shear and torsion combined, which is the MCFT method. So if you look at the part 8.1 0.2.7 of the code of AS5100, you will then see, instead of having an empirical formula, you will get a combined formula which has shear, torsion, bending together. So that allows you to look at for example, the bridge that I just showed had a 30-degree skew. So you will have torsion in some of the edge beams, etc., based on the skew. Correct. So then you'll be able to assess that torsion in the calculation. And we actually, so look, because of this update of the 2017 code, both the consultancy and also the asset owner start to investigate the difference, because we're trying to understand, does that mean the previous code is not good enough, and then what we have done in the past is now become an issue for performance. So they did a bit of investigation, and based on the study that we have done to date, the 2004 code can be a bit more conservative comparing to the 2017, because that was purely based on empirical, and then they had factors. The shear and torsion demand, it was slightly, for some bridge format, is slightly less conservative, because based on the particular bridge type, they will be able to consider the shear demand, the torsion demand, and the bending demand independently based on one formula. So you're no longer assuming a very conservative assumption for the shear demand or the torsion demand before you calculate the shear capacity based on the 2004 code. So yeah, so if you read the 5100 Part 5 2017 code, it will talk about MCFT. The research paper, if you want to dig in a little bit deeper, so it was basically Stratton tie model, looking at the shear transfer, the tension demand, very straightforward, like geometry, and they will have this, the research paper published by some Canadian researchers. So, and that was already adopted in the international code, and then the 2017 code then introduced this new clause here. So it is also new for us. So previously it was beautiful, just an Excel spreadsheet, you drag it down and you get all your calculations done. This one here, it takes a little bit more interaction between the different design actions, and then you have to size different load cases based on these corresponding actions with different critical load cases. So yeah.
So comparing to the empirical equation, this makes much more sense in terms of fundamental question. Otherwise it can be
Correct. So in terms of the empirical one previously, now obviously there's more research has been done, so they understand how the force gets transferred from the mid-span to the end span to the end support. So the way that they look at shear is more like reasonable, I would say, like rationally looking at how the load transfer and gets calculated. So that's definitely a sort of like a reasonable, like a rational approach, I would say. Yeah.
Yes.
So that long span Super T bridge, had it been a little bit longer, what was the next option for a bridge?
Okay. So
I'll just repeat.
okay. Yeah. Sorry. So another question was raised. Was if the longest Super T was a little bit longer, then what would be the next option here? Now that's a very interesting question. So to start with, I'll give you a bit more background. During tender design, it was never a single span. We had 3 span, 2 piers. So that was a 3 span, and then the pier was in between the railway. So that was the cheapest option that we can come up with. But then the stakeholder comes in and say, we want a beautiful clearance from one end to another end. That's it. We don't really care about the cost. So we had to try our best. And there was 2 challenges with this single span itself. Number one is nobody has done a single span pre-stress that is over 50 meters between bearings. So the sagging, the estimated sagging, was really challenging for us to estimate in the long term. The other challenge was that the road alignment of this bridge, you have the crown in the longitudinal direction. So it adds more thickness as an arch coming up and then the minimum thickness was at the breech end. So estimating that wet concrete and how much that composite action works in the long term was another beast. So that was a lot of challenge for us already. So having a slightly longer span, it is possible, but what's limiting it is actually the manufacturer's casting bed. So it's a bit of a commercial sensitive information that they may or may not want to release. Sometimes what you can then do is modify the casting bed and allow a few more meters, but as it gets even longer, then the problem is no longer sits with the manufacturer. It's more to do with your deflection, your bending, because as you can see from one of the oh, sorry, how do I do this? Go back to here. Do I do? Okay.
What I might do is just share the whole screen, that way.
Okay.
Okay.
Yep. So, if I show you quickly the cross section of the beam. So basically, this is the number of the strands here, and then you have some corner bars, reinforcement bars, and then you have some crack control bars on the top. So the number of the strand is almost fully utilized. What does that mean is, with a longer span, you will then end up with even higher bending moment, a higher demand of strength. Unless then your beam will be even thicker, so you get more iterations, etc., etc. Then it may not be cost effective anymore based on the site condition, lifting, etc. So the next option you will then consider is shortening the span length by introducing the intermediate support like we did. That was cheaper, and otherwise you will then change the bridge type. So there's many different other ways that you will be able to do. For example, a steel truss if the client is okay with maintenance, or you can do cable stayed bridges, other different forms. So the Super T has its merit because Australia have been building them, and we have been trusting them. It has been worked very well, and it's a very cost-effective product. So we're trying to utilize it as many as we can for a big tender design when you're trying to provide a cost-effective method. Whereas a cable stayed bridge, it's more glorious, it's beautiful, it's famous, but it has to come from the client side. This is another layer of the contracting and tendering is when the client wants something that is adding more intrinsic value to the community, then they are the one take the initiative, engage with the architects at the earlier stage of the design, and then tender that out and tell us this is the bridge type they want. Then we will be able to size it accordingly. But when you just be given a point A, a point B, link them together, this is when you're trying to use your imagination with Super Ts or the span types and trying to play with the most effective options. Because you also got to understand that a lot of the construction teams are familiar with the delivery and installation of the Super Ts, but when it comes to cable stayed bridges, you're talking about specialized teams, international support, proprietary products, and special maintenance strategy. So that's another different type of complexity that you're talking about. Yeah.
Very interesting. What we might do is leave the questions there. If there's further ones that come up that you would like, you can email them to me and I'll forward them on to Sean. But look, Sean, we really appreciated the lecture today. Really interesting information, some great career advice. So thank you again for coming and speaking to us. So we might have just 2 minutes and I'll get set up and we'll talk through your task 4. So thanks again, Sean. Really appreciate it. Thank you. Okay, excellent. We might keep powering through. I've got a reasonable amount of content, so I'll do the best I can. We went a little bit over time with Sean, but I thought it was really interesting, so we left it go. So Sean gave a great overview and dive into what it is to design a Super T bridge from a structural perspective, and I think that was really valuable. For our task, we've really taken a pretty significant step back from the detail that was discussed and are tackling it a bit more from a construction perspective. So maybe before I get started, hands up who's read task 4. Oh wow, yes, excellent. Okay, we're winning. So fantastic. I can skip over a little bit of that then. So what I'm going to talk about today is really quick intro to task 4, what it's all about. I'm then going to dive into the pile design calculations because that's probably the only component that hasn't really been presented in this subject as yet, and really give you a bit of an overview as to what you're doing, what the expectations are leading into this week's workshop. So workshops are running this week. Great, so we'll have a look at the site, what we're doing, I've discussed the geotechnical conditions we're working with, looking at some foundation options. You're doing a little mini optioneering. There's been lots of optioneering in this subject. You're doing a small one for the pile design. We'll talk a little bit about how you do a pile design from a high level and then give you some just rules of thumb for this subject. So this subject obviously is not geotechnical applications. We're not going into deep, detailed settlement analysis for foundations or anything like that. We'll just give you some really simple rules of thumb to do an option assessment and pick an appropriate foundation type. We're doing that because it's a construction and we're worried about how we're going to go about constructing, estimating costs, those jobs that are more in the realm of a construction engineer. We'll have some Q&A at the end as well, hopefully, if we get through this in a reasonable amount of time. So the task itself is focused around a single overpass. That overpass is in, or around, I should say, Ararat. You'll be overpassing a highway and a rail, both. And so Sean gave us some really good hints as to what might be a cost-effective solution for that using Super Ts. You're told you must use Super Ts. There's not really that much design scope to vary that bridge structure. And it is a skew overpass, so it's approaching what it's spanning at an angle like this photo here shows. Although this one's fairly different because we're only spanning across what looks to be a freeway there. But the road itself, the overpass itself, and these dimensions here are exactly what's specified for your assessment. So that's that width, that road is what you'll be designing for, essentially. So that's, this is on My Social Viewpoint. You've got this link. This is an overview of the initial concepts of alignment for the bypass. So a bypass just goes around a town so that you haven't got big freight and all this traffic going through a town. Ararat's in North Victoria, and this was proposed quite some time back as a alternate for the Western Highway to basically go around Ararat. You can see two different alignments proposed, a green and an orange. We're not going to really get into the alignment. We've looked already at that type optioneering this subject to some extent already. So we've picked the green alignment. That's the one we're going to design for. As a little bit of background, and again beyond scope for this subject, this project's had major delays principally because of cultural issues that were mismanaged at the start of the project. So if you're interested in that, look it up. We are sort of setting that aside and saying, well, we're just going to focus on the engineering of this project and use it as a mini case study. So, but we are bearing in mind there has been some mismanagement of this project from the start, which is why maybe it hasn't progressed on schedule. Anyway, that aside, green alignment is what we'll be looking at. There's 7 work packages, which I know look a little bit daunting. Some of these are not as significant. This assessment is worth 30%, so it's quite a considerable one, and I think it culminates a lot of what we've done in this subject and brings it all together in different ways. So I hope you enjoy going through the task. I know it's a lot of work, but hopefully it'll be a bit of fun bringing it all together as a team and coming up with what is a really holistic recommendation for this bypass. To do that recommendation, you need some basic concept works, just like you did for task 3. A bit simpler than task 3 in most respects. We're looking at a bit of sediment basin and retention basin design, which James has kindly prepared all the material for. It's pretty simple in terms of the hydrology, but you'll need to look a little bit about the geometry of your basins for the earthworks. And that is the work package 3, the earthworks component for those basins. So you're going to use bulldozers, excavators, how many do you need, how are you going to move the soil, and hopefully the previous workshop should facilitate those calculations. Work package 4 and 5 are around the substructure for the bridge, so the piles and options. That's what I'll talk about today. Doing a little bit of costing on those and picking and recommending an appropriate pile method to the client. So saying, right, we recommend precast piles or CFA piles or board piles for the following reasons. Work package 6 is construction methods. We want you to go through from a high level how the bridge will be constructed. Jeff Taplin's the lecture for that. He basically just presented it for you, but you need to obviously digest that and replicate it for your particular overpass. Finally, we want you to go through a mini costing exercise to cost the project, or this specific overpass, I should say. You're not doing all the other overpasses for the client. So really trying to bring together a lot of the components for the subject. So let's hone in on the pile and the geotechnical implications. So a few things, high level, more interest than actual calculation-wise, but there's no time-dependent consolidation required for the project, so that's definitely beyond scope for your specifying. We've got sand near the surface. We know from our first few weeks with Nick Morgan and a few other lecturers talking about boring piles in sand can be tricky because the sand just keeps falling in the hole. So there's ways and means. Drilling fluid is one of those means. I've got a slide on the geology, but we've got basically sand overlying some extremely weathered basalt that then improves at depth. So if we drive piles into ground, they'll meet refusal, so won't be able to hammer them in anymore once they start to hit that rock, which makes sense. Board piles, we'd likely need to drill a bit into that moderately weathered basalt to get enough capacity out of them. So just high level, that's what we're thinking. You'll be assessing each of those. So assessing foundation types, 2 assessments, as Sean actually mentioned, and as you've probably already done lots in structural engineering, we look at limit state and serviceability. So they're the 2 key components. For limit state, we'll do a little bit in the workshop this week. We have a safety reduction factor, Thi-G. That's a significant part of the work is calculating Thi-G. Thi-G depends on the risks associated with this job and how much uncertainty we have. Have we used rules of thumb to estimate capacities? Have we not really done much geotechnical investigation? Is nobody going to be monitoring what's happening on site? If all those things are sort of the case, we'd be very conservative and have a low Thi-G factor. Factor down our calculated capacities because we're just unsure. Conversely, if we've gone through, done lots of soil samples, have really good confidence in the geology, are using sophisticated design methods and have an engineer out on site monitoring the install, we can be less conservative about our reduction factor. So we'll calculate that in the workshop. It's not difficult, but there's a few factors that feed into that. We multiply a safety reduction factor by our calculated capacity. RUG, and G is standing for geotechnical. We obviously make sure our factor capacity is greater than our limit state load, just like structural engineering, the same concepts. Serviceability limit state, we'll do some really rules of thumb calculations for this and no detailed assessments really. I think we provide the serviceability limit state capacities for some of the foundations. Speaking of which, so the square precast piles that we hammer into ground, we talked about earlier on in this subject, we've provided you those working loads. Typically we just drive those piles until they meet refusal, in this instance on the basalt. So once we keep hammering them and they're not going in any further, or not going in more than 2.5 centimetres in 10 hits, then we say, great, that pile's been driven to refusal. We typically would do some PDA testing, make sure that we haven't broken the pile when driving it in the ground, and make sure that we've got the capacity that we need, and I've got some photos of that shortly. Another test that we do when we're driving a pile in the ground, we've got the opportunity to test the capacity of that pile through dynamic pile testing. So we put some instrumentation on the pile itself, we hit it with the hammer, and based on that response we can calculate the capacity of the pile. This can be done for not only square precast piles but also board piles or CFA piles by hitting the pile with a big hammer, measuring that response and understanding then from that response what the capacity and integrity of our pile is. So here's another example on a larger pile. This looks like a board pile probably. Got some instrumentation there on the pile, and there's the giant test hammer. So that giant test hammer will just be released, that weight will come down and smack the pile really hard, and based on those responses we know, great, our pile can handle 2 meganewtons, 3 meganewtons or whatever it might be. It gives us a good indication of the pile's performance. You might say, why bother? We've designed our pile, why bother test? Well, testing obviously gives us a surety of the capacity that we want has been met, and we actually get benefits to testing. If we go back to our original formula, this Thi-G has a constituent that's factored from testing. So if we test 10% of piles, 5% of piles, we get a big benefit to design. So if we start testing some piles, it means on our overall project we might just need to install less piles or less deep piles and therefore save money on our foundation system just because we're testing some. So the Australian Standards gives back benefits to the designer for doing these due diligence things like testing in order to make sure it's a safe design, but it factors back for us. So it might be something you specify in your task for. Yes, let's test 5% of piles. You will then use that factor to calculate your Thi-G. Here's another example of this one's testing a cast board pile, for example, but the concept's exactly the same. So what we run through now, and you've already had some of this talked about, at least from a conceptual level, but in today's talk I'll talk also about the capacities of these systems. So board piles, think of board piles as we're just digging earth out of the ground. We end up with a hole in the ground, we fill that with reinforcement and then concrete. That's really all a board pile is. If we're dealing with sand or unsupported loose material, it's a hassle because it'll keep falling in the hole as we're digging the hole out. We can use bentonite slurry or one of those steel tubes that we drive into ground first to mitigate that problem. Great thing about board piles is we can dig into nice strong rock and create really strong big piles for large loads. Here's an example whereby tubes are driven to help support the top layers of the soil from collapsing into the hole, and then we've got a rock socket that can then bore into the rock and create a rock socketed pile, which you've got in this task. So you are doing rock socketed board piles and CFA tiles because they're socketed into that basalt. Here's another example of a board pile. This is down on the Yarra. You can still see big steel tubes that help support the hole again, and drilling into some really mucky sort of material. They'll be using board piles. They'll be going right down into the siltstone distillery in there, I would imagine, to get enough capacity for this bridge. But that soft upper layer presents the problem, which is why you need that shield. Our next type of piles, CFA. We've heard all about CFA heaps. They're smaller typically than our board pile, but we've got a lot of expertise in Melbourne. They can be done quite deep and are becoming more significant for larger loads. This is a giant corkscrew. We drive that corkscrew in the ground. No soils come out of the ground yet. We then start injecting concrete through the centre of that corkscrew and pull it out of the ground, and what we end up with is a hole full of concrete. We then lower reinforcement into that hole and we've got a pile. The problem with this, or the challenges I should say, is you're not drilling into a whole lot of rock with this, because imagine trying to drive your corkscrew into 10 metres of rock. It's just not reasonable. A bored pile can dig out rock because it does a little bit at a time. So this method is only good for into extremely weathered to maybe a little bit of moderately weathered rock, a few metres at tops. Great thing about this one is you won't have to worry about that sand because your pole's never not supported. So it will be cheaper and more economical per pile by far to do a CFA than a bored pile. In all scenarios, generally speaking, but especially scenarios where your material is not self-supporting. Here's another giant rig, that's a particularly big one. Here's some examples on a bridge abutment. You see lots of alluvial, great application for a CFA pile. Some more steel tubes in a marine application driven into the ground, and again you would excavate the material in those tubes. Some tables, basically you'll be doing a bit of this assessment in your task, but looking at the different pile types. So preformed or precast piles, they're relatively cost effective. They're good quality because they're made in a factory, but they're noisy to install. Do you care out in Ararat's bypass? Probably not. Noise might not be that big a deal out there. You're a long way from any residences, so maybe that's not a big impact. Enlarged base piles are very uncommon now, so I don't think we need to even talk about them to a large degree. And H open low displacement piles are also uncommon because they're too expensive. Non-displacement piles, so piles where you dig out the material. Bored piles, high capacity but more expensive. CFA, quicker, not quite as strong, can be hard to install our reinforcement cage really deep. Design values. Okay, so this is where we get to the nitty-gritty of it, I guess. And this is the calculations that you will be doing in task 4. So there's lots of values here, and I've kind of put everything in this presentation so that you've got a little mini toolkit after. If you're looking at some geotech stuff and thinking, gosh, I can't remember any of these design values, you can go back to this slide. Most of it's irrelevant for you for this task, but for this task you're going to be using for the rock socket and bearing of 5 times the compressive strength of the rock and a shaft friction of 0.45 times the square root of that strength of the rock. So the deeper it goes, the more shaft friction you've got on the rock, but the end bearing capacity is dependent on obviously the rock strength that your pile is ending up in. And that's a stress, so stresses are multiplied by area. We'll do some of it in the workshop. And we'll come back to talking about that a bit more shortly. So pile types in Melbourne, we're well across those, I think. Let's talk a little bit about some of the on-site testing that you can do. So let's say we've won the tender for this Ararat bypass. We want to then go into a bit more detailed design. What might we do? We might send out a CPT rig to do some more accurate on-site, in-situ investigation. Let's work out how the soil material actually is out there. CPT just drives a cone into the ground and measures the resistance of driving that cone or that rod into the ground continuously over the depth. That will tell you, or can be related back to how a pile would perform in the same material. So these formulas are non-examinable and you won't be doing them in your task, but again, I've put them all here so that you've got them for reference in the future. But think of this as a really comprehensive in situ method of testing the geotechnical conditions. Okay. So, pile shaft friction, obviously along the sides of our pile we've got resistance from whether it be clay or rock or sand, and there's a variety of formulas to calculate those. For this task, we're only asking you to assess the resistance from the rock socket in those bored and CFA piles. So those previous 2 red formulas that I showed are the ones you're using. You're not worried about the rest of the shaft. All those frictions. Now this is examinable back to your rock socketed pile. On the x-axis, we have displacement, so how far the pile moves. On the y-axis, we have resistance. So if we want to design a bridge to not move a lot once we load it up, we want high resistance at low displacement to meet those serviceability requirements. So what type resistance should we be relying on here? Looking at this graph, for serviceability, what do you think we're going to choose to design for? Shaft resistance or base resistance, or a combination? Which would you rely on for serviceability? That's spot on, yes, shaft. Correct. Because let's say this is our serviceability limit of 1%. We move this pile across our 1%. What resistances are we getting? We get a little bit of base resistance, but not very much. We're getting almost all our shaft resistance at that 1%. Picturing it, what it means is the pile's gripping the edges of that rock socket really tightly, but it actually has to move quite a bit to start pushing on the bottom of the pile into the rock. Up to 10% the diameter, so if you've got a 1 metre across pile, it's moving 10 centimetres before it's activating that full bottom resistance. For limit state, that's great. It doesn't matter if our bridge moves down 10 centimetres before it collapses. That's not the end of the world. But for serviceability, that's obviously not acceptable. So 2 different design parameters, and we've actually made it pretty simple for you, task 4. For serviceability limit state, you just design for shaft resistance, period. You don't include base resistance. For limit state, you include serviceability, you include shaft resistance plus base resistance, which makes sense, hopefully. So, a bit more on the socket design itself, because that's obviously critical for a rock socket. Once you drill out a pile, the bottom of that socket's not like perfectly clean, smooth rock, is it? You've got bits of mud that are kind of fallen in there, other bits of debris, and that's, to a large extent, what incorporates or what leads to the fact that you need so much displacement to get that resistance. Okay, I think we've already said all this. Okay. So what about the socket itself? What might be important from a construction and design perspective to get that capacity out of the socket? There's been some fantastic research done into the shaft resistance versus a variety of different parameters. And this is, I guess, a little bit detailed, but I think the concepts are really quite interesting. Again, x-axis displacement, y-axis resistance. So bigger pile, smaller pile. Smaller piles develop these shaft resistances much faster than bigger piles. So a little pile will get, big resistances in terms of stress far earlier than a larger diameter pile. If we roughen the socket, so sometimes on a pile boring rig you'll see an extra tooth that sort of sticks out the side a bit to roughen that socket up. A rougher socket will obviously help grip the pile more and we'll get stressor earlier. If we put pressure in the concrete as we're pumping it into that pile, we'll get greater shaft resistance earlier as well. Finally, if we clean the edges of it nicely, we get far better shaft resistance far earlier, to the point whereby often designers will specify that this needs to be done. If you look, for example, if we've got smeared mud on the side of our socket of 10 millimetres, you're getting almost no shaft resistance, of course, because it's just sliding on the sides of that socket on the mud. So a clean socket or a cleaner is critical to get these resistances. And the same for drilling fluid. So if we're drilling under bentonite slurry, we don't just leave the slurry in there and cast the concrete. We want to have it cleaned out to a reasonable degree in order to get greater resistance earlier. So end bearing, in rock, I think we've specified 5 times the UCS. There's some other formulas there for you if you're working in other materials or other things for future reference. Socket capacity, here it is here, shaft friction, 0.45 times the square root of the UCS. Pretty simple. So pile load settlement, this is here for your reference again and is not examinable in the subject or the task. But for a comprehensive reference sheet, I'll put it in here for you, alongside train impact loading. So often what will govern these bridge designs or the piers of these bridges is impact. So what if the train comes off the rail and smacks into your pier? That's a really big load. So it might not be these vertical structural loads that you're supporting. It might be actually that train impact loading that mandates the size of those piers or the loads that you're dealing with. So you can see here, 4,000 kilonewtons longitudinal and 1,500 lateral, 2 metres above the track level. So that's a pretty serious load to design for. Again, your task 4, you're not going down that degree of detail, so you don't need to design for that, but it's well worth being aware that's often a critical point for your design. Negative skin friction, again, non-examinable, but something that is a factor that's worth considering, or needs to be considered, I should say, for pile design. Negative skin friction is where our soil material can drag down the pile itself, especially if it's non-consolidated, so that can be something that you need to factor in your considerations. So, there's some references there that, for further reading if you're working in this space that are of use, hopefully. All right, the next section is about the estimates around these piles. So let's say you've done some basic estimates on the capacities of precast piles, CFA piles, and bored rock-socketed piles. Your bored rock-socketed pile will be the strongest because it's bigger and deeper into stronger rock. Your CFA pile will be next up because it's not as deep into the stronger rock and it's a bit smaller. And your precast pile will be the lowest capacity, but they're cheaper per unit. So you've got to somehow figure out, what do I recommend for this project? Which pile type? You will know how many of each you need for your bridge based on either serviceability or limit state. Typically, serviceability will dictate the number of piles for your foundation capacity, but sometimes limit state. In order to make that recommendation, you should look at the costs and other implications. So we'll do a little mini MCA for this task. Cost is probably your main factor, given this isn't like in an urban setting or it's not got a lot of externalities right around the site itself. So we do a cost assessment. There's a few things that go into cost, obviously. We've got the materials themselves, but some intricacies with each pile system. So for precast pile, if you've got a 20 metre precast pile, you're not bringing a 20 metre precast pile in the back of the truck and trying to hammer a giant 20 metre pile into the ground. We need to join them together. So typically at about the 12 metre mark would be as long as we'd want to get a single element, and we'd be jointing ones that are any longer than that. That being said, if you were looking at driving piles to around a 16, 18 metre mark, it might make sense to have piles of around a 9 metres and hammer one 9 metre pile in, join another 9 metre pile, and then hammer that one in on top until you're obviously getting refusal. So we've given you some costs here. Supply and drive, $128 per metre plus the joints. We've given you some timing as well and some design loads. So ultimate limit state 3 meganewtons, working load 1.8 meganewtons. So there's not a lot of calculations that need to be done here. This is for your geotechnical design capacity. CFA piles, these are now specified in dollars per cubic metre of pile because your principal costs are around your reinforcement and your concrete themselves. You can do 100 metres, linear metres per 10-hour shift, so that's 100 metres of pile length. We're drilling these into the extremely weathered basalt, and again, our settlement criteria less than 1% pile diameter. To comply with this, what you'll be doing your comparison on is the serviceability limit state load from your bridge, and you'll be comparing that and making sure that's less to or equal to your 0.45 times the square root of the UCS multiplied by your shaft area. So I'll just put SA here for shaft area. So that's your calculation that you're checking serviceability on. Pretty simple one, hopefully. Board rock socketed piles. Now we can see the costs going up, so we've gone from $460 per cubic metre to $1,500. So 3 times the cost per metre cubed, and they're bigger. So each pile is going to be, 5 or 6 times the cost at least compared to a CFA pile. Now, typically, a rig and team might do, if they're going pretty well, 1 rock socketed pile in a day. If things are going a little bit slower, maybe half a pile in a day. So it takes time. And it takes time because you're digging a bit of soil, bringing that up, putting it off to the side and dumping it on the ground, then putting the rig back in the ground and drilling out another little bit. And so, you've got to think of it as a really iterative process. It just takes time. If you're drilling rock, you don't drill rock really fast either. That takes time as well. So it is a slow process. However, it's unmatched in terms of capacity. If you need big loads and you want to socket them into strong rock, there's no choice. This is the method. This is the method that was employed in the Melbourne Metro Rail project, the Parkville station box. They were all board piles all around the edge. Does anyone know why they used board piles around that Melbourne Metro Rail project? A few of us went on the site tour. It was pretty interesting to see. What was the geology there for Parkville? Does anyone know? Yeah, Melbourne Formation. So we've got a lot of rock. Not super strong rock, but if you're drilling, what were they drilling, 40-ish metres, 30, 40 metres into this rock in various locations, a CFA rig's not drilling that far into rock. It's just ludicrous. So we have to have a board pile as soon as we're drilling into that stronger material for a reasonable depth. So design loads are typically governed by the structural strength of the pile. So something we haven't talked about, but I'm going to draw up on the overhead cam. Can I draw on the overhead camera? I don't think I can actually, can I? I might draw on a slide. Nobody can see it online otherwise. In design, we're obviously worried about how the geotechnical capacity of the pile, so that is the pile moving in the soil or rock material, and then the structural capacity of the pile. So think of it as a giant concrete column, that has a capacity as well. We have to take whichever is less for our critical design. Most of the time for CFA piles, it's not the structural capacity, it's the geotechnical capacity that limits our limit state design. However, if we're socketing a board pile into rock 4 or 5 metres, strong rock, that rock's not going anywhere, it's not moving. Our capacity is now limited, or typically limited, to the capacity of the concrete that we're cast there, not the rock itself. And you'll do that calculation in this task. It's a simple one, and it's the same as any calculation you've done for a concrete column, just summing the concrete capacity and the steel capacity times their areas. Obviously, again, reduced with a safety factor, but the same concepts. So, so you could be comparing both of those for a board rock-socketed pile. Okay, so precast Super T bridge, you've heard heaps about these. And there's a few videos. Please watch the craneage. If you've got your workshop straight after this, there's no time, don't worry. But if you've got your workshop either tonight or tomorrow, watch the craneage video that I've put up. I run through a placement of a Super T, how it's done, what some considerations are in that one. Today, instead, I just have I don't know if it's going to, maybe let's try and just grab. Yes, it will work, hopefully. We don't need lots of sound here. Okay. Have you seen this video? No? Great. Okay. Some lecturers end up showing it. So, I've gone past it. Sorry. Let's go again. Okay. This is not a Super T, obviously, but this is a precast concrete section. It's a shame it was filmed on an iPhone 3, but we get an idea of what can go wrong if the foundations aren't quite right. So you've got 2 cranes lifting this precast section from each side of the bridge. Here we go. Now this crane's got a bearing pad here. And you can see you've got movement under the wheel of this crane. Now, in the crane lecture, I talked a bit about, the things that you've got to watch out for crane design. One of the most critical ones is the preparation of the pad that the crane's lifting from. So in this instance, you can see that outrigger of the crane's pushing down into the softer material, and the beam's sort of getting lower and lower. Things are obviously not going very well. And until you get full bearing failure, yep, and over he goes. So obviously an example, pretty catastrophic failure in that instance. In talking with a lot of these construction companies, so Delta Group or any of the other tier 1 companies, the focus on these outrigger locations for the cranes is really critical, and it actually forms part of the design process to such an extent that often what will be done is a pile will be located just for that crane's outrigger. So you might go out on site, put in a CFA pile just where the outrigger is going to sit, so that outrigger can sit on a nice, strong surface and not have any risk of that. So obviously the assessment of these conditions is really important. Other examples of failures like this is when cranes are lifting on a superstructure, so on a bridge itself, and those outriggers just punching through the deck of the bridge can be an issue as well. So really important in your task for your specifying construction sequence. So I think probably saying, you know, assessing and designing for a crane pad would be an appropriate thing to be recommending in your design. So that video was a little bit out of place in the lecture, so sorry. But anyway, so things to consider when doing these estimations of piles, board piles, CFA piles, or your precast piles is, what are you doing them for? You're doing them for the piers of your bridge that are supporting your Super T. So that's what role these foundations are playing here. What sequence and what are the logistics? This bridge is not a top-down or anything, so your sequence will be your piles, your pile pads, your piers, your crosshead, and then your Super T's on top. Okay. Are you doing a single span or multi-span bridge? I don't know. You'll find out after your workshop for sure. And the detailed foundation design and cost comparison. I would not necessarily use the word detailed here, it's probably a little bit of a stretch. I'd say sort of a back-of-the-envelope foundation design and cost comparison for this task. Things to consider beyond just cost, timing. Are you going to get one done a week or two before the other? Maybe that's really important for your job. Local contractor skill sets or equipment's relevant too. You're in Ararat, you're not in Melbourne, so any big rigs you'll have to bring up from Melbourne. Maybe there's a local contractor with a precast set up there that might be cheaper. Typically you present your costs per unit, whether that be per linear metre or per metre cubed. Typically precast piles is per linear metre, and board and CFA piles are per cubic metre. That gives you a single metric to compare all pile types, so that you can look at somebody else's pile calculations and see, oh, it's this much per cubic metre, and you instantly can compare it to other jobs, rather than having per linear metre for a board pile that could be 750 in diameter or all 1.2 in diameter. So that's why a consistent unit's chosen, and you'll need to do this for your task 4. Here's some examples. Now I think I had a few calculation errors on some of these, so don't necessarily use this as a definitive, this is the calculation method, but rather a template for how it's often laid out as a cost comparison, because I'm sure I've made a couple of mistakes on some of these. An estimate would typically show a number of line items. Each of those line items represents an aspect of the job. You will notice here you've got establishing and demobilising the rig. So once you bringing that rig there and setting it up, you need to get it there on a truck or whatever it might be. You need often a crane to install the mast and the boom and the different bits of the rig. So this costs money and must be included. The joints for the piles are expensive. The concrete itself, the reinforcement, all have costs associated with it. If you're doing tests on them, that costs as well. So they need to be included. We typically add a margin, because the idea of a piling contractor is to actually make some money, and some contingency in case things go a little bit wrong. and that would obviously depend on the on-site risks for each job. You will do that for a precast, for a CFA, and for a rock-socketed pile. All these, yes?
I just noticed your margin change 15 to 20%. Is that common?
It's a good question. I don't have a definitive answer to. I can give you a guess as to why I think it's changed. There is driving a precast pile in the ground is not exactly a sophisticated setup. It basically got a cable and a hoist that hoists up a big weight and drops it on top of the pile, and you just keep dropping that weight on until the pile is deep enough in the ground. It's not a very expensive piece of equipment or machinery, so there's a lot of contractors out there that can tackle a job like that. Conversely, CFA piles, it's a pretty big rig and a pretty powerful one that needs to drive that screw all the way in the ground. There's less contractors, probably a little bit less competition in the marketplace, so it's possible that they can demand a little bit more margin on these jobs. That's my guess, but yeah.
But those margins of about 15-20%.
Oh, sorry, as an overall percent, yes, yeah, that is fairly, I mean, maybe the last year or two in construction, that's gone out the window, but typically, yes, that was a common percentage to have as a margin, yes. And the contingencies probably, I think you'd find that lately that contingency number will be significantly higher. From the builders I'm working with, they're adding in a bit of fat there because you just don't know in terms of both labour and subcontractors rates as well as materials. Just there's a lot of uncertainty in the market now, so you might find that those percentages have shifted considerably. So don't worry, there's only a couple more slides. I know everyone's probably itching to get a coffee before the workshop. So precast or in situ, this is what we're asking you of Task 4. Here are some factors that might be worth considering when making your recommendation to your client. I'll let you read them in your own time. Questions are welcome. Just before I finish up, this workshop this week, we'll be doing 3 things. You'll be looking at the concept of your overpass, just to get a feel for how it's going to look, what the clearances are, what the dimensions are. We'll be doing 1 mini crane chart reading for a particular lift of a Super T, and we'll do 1 sample calculation from these board piles to get a feel for the calculation process using the Australian standards. That should give you all the tools necessary for Task 4. Now, Task 4, well, there's no more workshops except this week on it, so we will have more and more consults. I'll get Richard online for it as well to help you through. It's a big task, and we've got a bit over 2.5 weeks. So yeah, we'll get stuck into it. But yeah, any questions before we wrap up today? Yes.
When you thought about the conceptual design, how detailed do we need to go through? Do we need to design for the reinforcement for the foundation and also for the bridge, or we don't need to?
Great question. Level of detail in the design is not to the degree of reinforcement. It's dimensional detail. So, how high is your bridge, how long, how wide, what Super Ts you're using, but definitely no reinforcement detailing or, say, parapet design or any of that. We're really 1 step back from that. It's really high-level conceptual design. Yes?
Do we need to do any modeling, like space-gas modeling to find out the...
No modelling expectations either, so yeah, you don't have to worry about that. Yeah, good questions though. Thanks everyone, see you in the workshops. Yeah. Is it possible to share the slides in Zoom? Oh, yes, okay. All right, thanks everyone online. I'll see you all in the workshops this week. Yes.
Question about the spans
Of course.
for the task. If we're finding that a critical span is essentially lengthened by one of the abutments,
Is what, sorry, length?
so like
Yes.
if it's like over the road,
Yep.
then like you obviously have to consider the abutment length.
Yes. The spill through. Yep.
Yeah. Can we add a? I guess it's a tough question. Do we have to the sort of frequent break? The frequent break in a half metre that we put on the bridge. Do we have to consider a similar sort of thing on